Okay, on this section of our lesson, I'm going to talk about the chemical synapse. Now, this is the synapse that we generally think of when we think of neurological synapses. There is another type of synapse, just to introduce it to you. I'm not going to go into it in any depth, but there is an electrical synapse as well. And if Guyton does talk briefly about the electrical synapse if you're interested, but you don't need to know about it for this lesson. So the chemical synapse. Now, just to orient you to where we are, here we have a presynaptic neuron and an action potential is traveling down the neuron. Now, it has to get across from this neuron. The message has to get across from this neuron into the postsynaptic neuron. So we have a presynaptic neuron and a postsynaptic neuron. So how does the message get from one side to the other? Well, it has to cross the chemical synapse. Now, I wanted to show that the chemical synapse between a presynaptic neuron and a postsynaptic neuron can occur in several different places. It could occur at the connection between an axon and a dendrite, way at the tip of the dendrite. It might be on the side of the dendrite, or it could connect the axon directly to the soma of the postsynaptic neuron. Now remember, in a typical neuron, there will be literally hundreds of axons connecting to this postsynaptic neuron all over the place. So one of the purposes of dendrites is just to increase the surface area so those hundreds of neurons can indeed all have places to connect. Okay, so that gives you a picture where we're at. Now we are going to talk about a specific one instance of a chemical synapse. Okay, so a chemical synapse occurs between a presynaptic neuron and a postsynaptic neuron. So the presynaptic and postsynaptic. Sorry, it's hard to read there. So presynaptic and postsynaptic. So the direction of the potential of the action potential is this way. So it has to get across here and then continue on. In order for the message to get from one place to another, it must cross this synapse. So just to give you some terminology, this membrane here is called the presynaptic membrane. Okay. This part of the axon is called the axon bouton. Bouton is just a fancy French word for button. And it's just a little area at the end of the axon that swells, that pouches out a little bit, and it gives room for various things to be stored there. For instance, the vesicles, which are storing neurotransmitters. So these vesicles with neurotransmitters are stored in the axon bouton. Now in between the, now here we have a postsynaptic membrane. And in between the two is the synaptic cleft. So the synaptic cleft is the space between the presynaptic membrane and the postsynaptic membrane. Okay, so how does an action potential move from one side to another? So we have this action potential that's moving down this axon, and remember what's occurring there is sodium is rushing into the cell and it's changing the polarity of the membrane from positive on the outside to negative on the inside to negative on the outside and positive on the inside. Now, I'm not going to go through all the steps of what occurs here, but suffice it to say that the change in voltage here down at the end of the axon in the bouton opens up calcium gates, and calcium rushes into the bouton, and when it rushes into the bouton, it causes the vesicles to fuse to the postsynaptic membrane, and that fusion causes the postsynaptic membrane to sort of open up in these areas, and that allows the neurotransmitter to be released. Now, the neurotransmitter, the most common one and the one I'm going to be talking about here, sort of the one that's used as an example most often, is acetylcholine. So we have acetylcholine that is being, the release trigger is the influx of calcium, and the trigger for that is the change of polarity of the membrane because of the action potential. And the calcium causes the vesicle to fuse to the presynaptic membrane, and that causes a release of the acetylcholine. So you have acetylcholine that enters the synaptic cleft. Now when it enters the synaptic cleft, some of it just floats around, but some of it happens to bump into these little areas that bind with it. Now, what are these little purple things here? These purple things are ligand-gated sodium channels. So what happens is the acetylcholine reversibly binds with the ligand-gated sodium channels, and that causes them to change shape. And you can guess what happens then. When they change shape, excuse me, that change in shape allows sodium to rush into the cell. Okay. Now, if enough sodium rushes into the cell, what's going to happen? It's going to trigger voltage-gated sodium channels to open up. And when voltage-gated channels open up, that triggers more sodium to enter the cell. And then we have the action potential propagating as it goes down, and starts off going down the postsynaptic neuron. Okay? Now, this reaction is only going to occur if enough sodium enters here. So enough acetylcholine has to be released at the presynaptic membrane to bind with enough of these ligand-gated sodium channels for enough sodium to enter the postsynaptic neuron to initiate the voltage-gated sodium channels to open up and start the propagation of the next action potential in the postsynaptic neuron. Okay, here in this picture, I want to talk about how things get interesting at the synapse. The synapse is the place in the nervous system where all of the information processing can take place. A nerve axon is really sort of a dumb entity. It only has two choices. It can either pass on a action potential, or it cannot pass it on. It doesn't. It's an all or nothing phenomenon. But a synapse is much more nuanced. It can choose sort of when to pass on action potentials and how many and what percentage of action potentials will be passed on from one nerve to the next. Okay, so the synapse is where all information processing occurs. Now, it occurs because of two phenomena. One is called summation. Now, remember, these ligand-gated sodium channels will open up in response to the presence of a neurotransmitter. All right. Now, the neurotransmitter has to be present in sufficient quantities to open up a significant number of the ligand-gated sodium channels. So if there's only a few, if there's a small concentration of acetylcholine, maybe only a small percentage of the ligand-gated sodium channels will open up. So only a small amount of sodium is going to enter the cell. Now maybe this is enough to say decrease the membrane voltage from negative 90 milliequivalents to negative 85. That's not enough to reach the threshold of this voltage-gated sodium channel here. Say the threshold of this voltage-gated sodium channel is negative 60. So, in order for the action potential to be transmitted from this side to the other side, we need more of these ligand-gated sodium channels to open up in order to get down to this threshold. Right? So how can that occur? Well, the process by which it occurs is called the process of summation. There's two different types of summation. There is temporal summation, and that relates to time. This can occur if there are dozens or hundreds of action potentials that occur in a short period of time. So say we get 12 action potentials that race down this nerve in 1 second. So this nerve has been activated a whole bunch of times. Each time that an action potential occurs, more of these vesicles are going to fuse with the presynaptic membrane, and more acetylcholine is going to get released. And that may allow more of these ligand-gated sodium channels to open up, and this may get it down to threshold. The other type of summation that can occur is spatial summation. And spatial summation means, whoops, didn't spell that right, spatial summation. Spatial summation occurs when over the entire postsynaptic neuron there are several different presynaptic neurons that connect to it, and each of these presynaptic membranes are firing off with action potentials, and that increases, and each of these separate presynaptic neurons are releasing a little bit of acetylcholine into the synaptic cleft, and that can increase the concentration and open up more ligand-gated sodium channels. So that's the process of summation. Temporal means there are more action potentials over a period of time. Spatial means that there are more action potentials over a specific spatial area. So there may be 12 presynaptic axons, each releasing their contents into the synaptic cleft. But you see what I'm saying? Sometimes one action potential from one nerve may not be sufficient in creating the concentration of acetylcholine necessary to open up a great enough number of these ligand-gated sodium channels to initiate the action potential, the propagation of the action potential in the postsynaptic neuron. Okay? All right, now the other concept that I wanted to talk about here is, in this case, we are talking about a theoretical threshold of a voltage of minus 60 for the action potential to continue. Now, interestingly enough, another way that information can be processed in neurons is there is a process called neuromodulation, which can occur because of the presence of different neurons that can either excite the membrane of the postsynaptic neuron or inhibit that membrane. So say I have an inhibitory postsynaptic nerve here. So this is delivering an inhibitory postsynaptic potential. Now what happens here is a neurotransmitter is released into the synaptic cleft here, and this neurotransmitter opens up a different type of ligand gate. And this ligand gate, since it's an inhibitory membrane, is going to allow chloride to enter. And chloride is an anion, so lots of chloride is entering, and that is going to hyperpolarize the membrane. So it's going to go from negative 90, from a resting potential of negative 90 to a resting potential of negative 110. That is going to make it more difficult. You're going to need more sodium. More sodium is going to be necessary to reach this threshold. Okay? So this neurotransmitter from this neuron is opening up a ligand gate, allowing chloride to enter, hyperpolarizing the membrane, and this is inhibiting the propagation of a new action potential by hyperpolarizing the membrane. Okay? And one of the major ways of doing that is by a ligand gate that allows chloride to enter. Okay? Now, this next neuron I'm going to talk about is, and will start an excitatory postsynaptic potential. Now, the excitatory postsynaptic potential also has little vesicles in it, and it releases neurotransmitters into the synaptic cleft, and this neurotransmitter will open up a ligand gate that will allow positive ions to enter, such as calcium. And this will hypopolarize the membrane because the inside becomes more positive, the outside becomes less negative. Less positive, and so it is hyperpolarizing the membrane. So maybe it's decreasing it to a resting potential of minus 80, and therefore this threshold potential will be easier to reach, and less sodium will need to enter, and fewer of these ligand-gated sodium channels will need to open in order to propagate a new action potential. Okay, so does that make sense? This is the way that a postsynaptic neuron can sort of make a decision whether or not to pass on an action potential. It makes a decision based on summation. It needs a certain number of action potentials to occur over time, or spatial summation. It needs a certain number of action potentials to be delivered from several different axons. And summation is influenced by the inhibitory postsynaptic potentials and the excitatory postsynaptic potentials. So these are all the factors that are involved in making that complex decision whether or not to pass on a new action potential. And this is a process called neuromodulation, and this is what makes our brain work as a brain. This is what allows us to process information rather than just pass it on blindly.